All right, so we're going to talk about work kinetic energy theorem. Before we get going here today, one thing that I feel like I don't do a great job of is I want to make sure that you guys have a good understanding of where we are at in the chapter currently. So I'm going to need your help remembering this too. I'm going to do my best, but what I want to do is two things as I wait for the screen to come up. The first thing is on Mondays, I always want to pull out. Do you guys use this document? You should. Okay. It tells you when I should be covering what topics, when labs are, when assignments for the most part are. They do get moved around just a little bit. So I want to make sure on Mondays that we're in the same spot. So the end of last week, we covered work. We talked about what work is. Friday, really touched right there at the end, the work kinetic energy theorem. We're going to hit that a lot stronger today in combination with energy practice right here. And we should have a lab over those things specifically tomorrow. Yeah. And we'll talk about types of energy right here, conservation of energy, work energy, and power. What you'll notice is that we are not too far away from the test. We actually have 4 days next week as it stands right now. And then your test is at the end. It's a week from Friday, okay, over energy. We're going to go relatively quickly through this energy section. Yeah, so are there any questions about this so far? Yes, sir.
If we do go remote, are we going to do labs online, or are we just going to have labs?
We're not going to go remote. That's my belief right now. It's my wholehearted belief right now. As far as whether or not we go remote, I'll address that when we get there. Okay. Quite frankly, I'll tell you the truth. If we go remote, this class is going to suck a lot more. It will. It's just not. It's not. Well, it's learning in general is going to be worse. I mean, don't get me wrong. Students that get excited about remote are really excited that class can't work the exact same way, and they get to play video games a lot more often, which is awesome for current you. For future you, it's absolutely horrible. Like Physics 2 right now is dealing with the fact that we didn't learn physics nearly as well last year, and you won't. So, again, I'm sorry, a long answer to your short question. But I'm going to proceed as though we don't need to and deal with that later on, because I don't answer your question. I don't know. I don't know. You don't have my equipment at your house. So to ask you to do labs online is, yeah, this class will, I mean, if you thought this class was hard when you're in person, just wait until we have to go remote and you have to try to understand the same sort of things. I mean, think about every time I try to have conversation, I have you guys have conversations with each other to understand your confusion. I was just yelling at first hour because today's lesson is kind of confusing. And I looked out across first hour and I could see confused eyes. I could see them. But they said jack squat to me. And I hate that because I have no idea how to help them. 0% idea how to help students who aren't answering questions. And if you're not here in person, that becomes even harder. All right. So the first thing I want to do is go over this on Mondays. The second thing I just want to make sure and do is at the beginning of every lesson, I want to tell you what the purpose is for today. Okay. So to talk about what we've done so far, this was an introduction of what work is, very conceptually. The second day was kind of heading into more the mathematical side of what work is and how we can get numbers associated with it. Humor me real quick. We should know what is work? Change energy. It's how we change energy from one form specifically to another form. Right. And then how do we calculate that? Well, what's the equation for work? Cosine angle, or you can say force times displacement that is already parallel to that particular force, as we saw specifically on Friday. Today's purpose is to review kinetic energy and talk about the work kinetic energy theorem, and then we'll have a lab tomorrow, and then we'll somewhat be done with this stuff because I don't have time. I mean, there's too much content to cover to just kind of sit around with some of these things, which is why it is so important for you guys to ask good questions when you don't understand. And for the most part, I'll tell you, this class is usually really darn good at it. Okay, I think it helps that it's a little bit smaller. But yeah, okay. Do you think that's helpful? Yes, no, indifferent, what? All right, let's talk. Let's erase the stuff that we have up here so far. I know. I think it was Alyssa, were we talking the other day about how it looks very intimidating when you see the leftover stuff from first hour?
Every time I walk in, I get so scared because it's just whenever you look at it and you don't know what's
Right. Well,
going
yeah.
on, oh my gosh, it stresses me out. You should just erase it before I come in.
I do my best to. I try to, but I don't always remember. All right, let's make sure I'm on the screen here. Okay. So what we ended with on Friday, just a quick review, is I said, hey, right, we're talking about the difference between those two, energy, change, and energy. You've answered this question like 9 times. Let's do a 10th. Which one of these have we focused on to begin with? The change in energy, which of course I would then ask is what? You'd say work. And the reason why, as you've already answered, is there's about 11 different types of energy. So what we, at the end of Friday, discussed is what is the main type of that energy, or just one of these specific types of energy. So just one of those types of energy. And the second thing that I remember to tell you is that, hey, if you watch speed, essentially that, informs energy. Meaning, which has more energy? This sitting here right here, or it moving? Moving. The more speed it has. And I'll point out to you guys that I asked you guys a series of questions about this, and you already answered them before I told you anything. Before I told you absolutely anything about energy, you answered them correctly, and for the most part, you were doing this. Well, this also directly goes into that type of energy that we were talking at the very end, which of course was kinetic energy, or the energy of motion. And I think this class actually did get, you guys are a little bit ahead of first hour right now, but you guys did get to the equation, correct? What is the equation for kinetic energy? Right, and it's kind of confusing because obviously it's a V, but what is that actually? Speed, correct. That is the speed. Make sure in your notes that you mention that to yourself because it's very, very confusing. I apologize, it's the notation that comes out of that. So this is the main type of energy, right? So you can see from this, by the way, if you have an object, will it have mass? So if I talk about an object's kinetic energy, that is not going to be 0. So basically, when will kinetic energy be 0? Yeah, the only other variable there is speed. So if speed is 0, kinetic energy will be 0, and vice versa with one another. Now, as energy is scalar, does it matter which direction I'm going, left, right, up, down, front, back? No. If I start having a certain amount of mass and going this way at 1 meter per second, and then I go this way at 1 meter per second, do those kinetic energies differ from one another? Absolutely not. Okay. And we talked, I know, a little bit on Friday about how if you double the speed, what happens to kinetic energy?
It's
4 times as much. Do you remember why? Do we have any questions about why there? Are we good there? Okay, it's because of the squared right here, right? If you think all the other numbers are going to stay the same, like let's say I was talking about mass first, not speed. If I double the mass, what should happen to kinetic energy? It should double. The main thing that you're going to look at is what is the power on that guy right there. If I multiply that by 2, then this goes up by 2. On the other hand, speed has a squared on it. So if I double speed, because of the squared, kinetic energy doesn't go up by 2, it goes up by 4. Or, humor me, if I then triple speed, kinetic energy should go up by, nope, 9, but it's squared. 3 times 3, 9, right? Go up by 4, 16, 5, 25, you get the general idea. It goes up really darn fast because of that particular square, okay? A way that you could kind of understand that is, well, how do we change energy? How do we change an object's energy?
Is that changing the direction?
No. Come on. We spent 3 days on this. It makes me sad. It's, how do you change an object's energy? Change in energy is defined as
Speed?
I think you're going to be sad when you. How do you? Let me write it out. Hey guys, how do you change an object's energy?
work.
There it is. So only we spent 3 days on it. Yeah, we change an object's energy through work. So let's say a car is barreling down the road. Okay, it's going down the road. Does it have kinetic energy? Yeah, absolutely. It has a good amount of mass and more than likely a good amount of speed, right? If you want that car then to come to a stop in terms of energy, you have to do, you're going to change its energy, you got to do work, right? To take it away. So what three things are necessary to do work? So here's a car. Here we go. I got you. Okay. Car. There we go. We got a van. Here's my van. Travel. All right, it's going down the road. It's got a certain amount of kinetic energy, right? We want it to come to a stop. What do you got to do? Think simply first. Don't think energy first. What would you do to stop the car? Brakes. You press the brakes. Okay. In terms of energy, how does that do work? Well, what are the three things necessary for work? Force, which in this case would be because of brakes, right? Displacement, and they got to go the same way, right? So here's the car. You hit the brakes. Is the displacement that way? Yes. Okay. Is the force that way? Yes. So what kind of work is being done? Negative work. So does that make sense that it's taking energy away from this and therefore it should get less kinetic energy? Yes. Now let me ask you this to discuss in your groups real quick. Let's say I've got a particular speed and then I hit the brakes and I stop and we measure that displacement. Okay? Then I have the car do it again, but they double their speed. What should we find about their displacement? Discuss. All right, what'd you get? Not twice as long. Maybe 4 times as long. Why? Right. This is why it's really, really important for all of these pieces that you learn them very, very well and ask questions if you're anywhere confused. Because what you're hopefully starting to see, especially in energy, is like this small piece of work by itself, relatively easy conversation. I think you guys are doing pretty well on it. But now we have to combine it with kinetic energy and the understanding of kind of motion. So yeah, if this car doubled its speed, right, we just learned that its kinetic energy would quadruple, multiplied by 4. So the amount of work I have to do multiplies by 4. So if I use the exact same force, then the displacement has to be 4 times further. Does that make sense? Okay. Let's do this. Let's get some practice in here. Okay. Let's say we have a conveyor belt. Okay. And on said conveyor belt is a box. All right, so we have a box. That box will be a mass of 30 kilograms. And we'll say the conveyor belt is traveling at a speed of 0.5 meter per second. Humor me real quick. Calculate the kinetic energy of this. Now, this is a very, very simple thing. It's plug and chug. I get that. But please make sure to show the appropriate work here, okay? If you ever forget what I want as far as appropriate work is concerned, don't forget this. We talked about this at the beginning of the year. Do you use this at all? Do you remember this, Jafeeps? Given, find, equation, algebra, plug in, and then solve. So I write my given, right? Trying to find kinetic energy. What equation should you be using? Do I need to do any algebra? Nope, because kinetic energy is already by itself, so I can then plug in. Now, when you plug in, a couple major things I want to point out in just a second. What should you get? 3.75 joules. Here are the major things that for simple problems, okay? I'm even going to ignore if you don't do the given and find over here, Okay, but two major things I want to make sure, bare minimum, are on your equations always. One, you should write down the equation. Why? Because that tells the reader what you're specifically using, or more importantly, it tells you what you used to solve this thing. It reminds you, this is what I'm choosing to use for this situation. Okay? Of course, when things get more complicated, that will help you to remember that in the future. The second thing that you need to make sure to do bare minimum is always have units if you write a number. Okay? I never want to see this. Like if this problem was in your homework, I don't want to see this. Come on. A, it would not take that much more time to do this correctly. And B, I mean, that's bare minimum. So, all right, let's address this real quick. I think I kind of got away from it a second ago, and it's the units of kinetic energy. Well, for starters, it is an energy, so it should be in joules. But let's make sure we understand that because the units are entirely different. Where did the unit of the joule come from?
So they didn't want to write out all the, like...
What equation did we use to get the joule? Do you remember? It was the very first equation we discussed in here in this chapter. By definition, work. Correct. The equation for work was work is equal to force parallel to displacement. Right? And so work, the change in energy, remember you can essentially replace that with change in energy. What are the units of force? Newtons. And what are the units of meters? Sorry, I messed that up. What are the units for displacement? Meters. So a joule is actually a Newton meter. But remember, a Newton actually is what units? Not quite. Where did the Newton come from?
Is it like the kilogram times meters per second?
Very good. It came from Newton's second law. A kilogram times meter per second squared. So this is actually a kilogram times meter per second squared times a meter. So a joule is actually a kilogram times meter squared over second squared. Make sense? Okay. So you could see a joule either as Newton times meter, which will happen, or you could see it as a kilogram times meter squared over second squared. If we step back to kinetic energy, let's see the units of kinetic energy. Well, 1/2 has no units. Mass has the units of kilograms. Speed has the units of meters per second. And since speed is squared, both of these are squared. And hopefully you see that, yep, this is in fact still a joule. Cool beans? Okay. So far we've done things relatively easily. Let's step it up a little bit of a notch here. Okay. What I wanted to actually let's do this. So this box is traveling with a kinetic energy of 3.75 joules. So discuss in your group what would have to happen to this box then to get it to stop. In terms of energy, what would have to happen to the box in order to get it to stop? Discuss. Xavier, why don't actually real quick, Xavier, I want to mention real quick about a couple things. I don't know if you noticed that some of us shared it.
Yes.
I'm just saying right there that your work is starting to get less and less. So let's just make sure we're careful about that.
Yeah, I mean, in terms of what bare minimum you say, I at least want you to write what equation you're specifically using. One thing that I noticed on your work the other day that you're kind of stepping out on is cosine. Even if you know that it's cosine 0 or 1, a good way to show that kind of mathematically is something that let's say times 1. Obviously not necessary for mathematical purposes, but it reminds the reader essentially that you know where the angle is. Okay. Second thing, well, I think that several of theirs are not right, or I don't know if you're making them up or doing them, which is good to a certain degree, but I want you to make sure to fix those. Homework anything later.
It would just have to be like...
No, I put it in. This is just a reminder somewhat for them. Yes, please. All right, what you got? Yes.
Oh, really quick. I did my vocab, but I didn't know if I could just show you it. And
You always can. Yeah. So we'll do it right now, just towards the end of class. Just show it to me before you go, and I'll get it in. Yeah. Anytime the whole vocab is due and you want to keep it in your notebook, just show me at the beginning, and we'll get it taken care of. All right. So what would you have to do to this box to get it to stop? Okay, so I think you're going to go more specific even than I was. So in other words, you'd have to do what to it? You're describing what? You're doing, yes, you'd have to do negative work. Exactly how much work would you have to do? Negative 3.75 to get it to stop, right? I say that to you to then show you this equation. This is ultimately where we're headed, okay? What we see is that the work net, you add up all of the works, they are equal to the change in kinetic energy. This is what's known as the work kinetic energy theorem. This is the first big equation. I say big equation because you've obviously already seen two other equations, or actually arguably 3 or 4, in this chapter. But this is kind of where we were trying to get headed to. This is the, you know how like in forces, you pretty much always started with Newton's second law? Like you did a force diagram, and then you do sum of forces in the x, sum of forces in the y, okay? There are two big equations in energy. This is the first one. All right, so let's show you this equation in terms of what I just said. Okay, what I just said was if an object has 3.75 joules, what would we have to do to it to get it to stop? Well, note carefully that this is not kinetic energy. This is the change in kinetic energy. So you'll notice it is not equal to 1/2 mv squared. How do you get the change in anything? Change in velocity, change in displacement, change in...
final minus the initial.
Correct. So technically there are two kinetic energies here. It's work net equals kinetic energy final minus kinetic energy initial. In the example we were just talking about, this 3.75 would be what? Initial, correct. It would be right there. And I said I would want to get it to a stop, which would mean that the final would be 0. And hopefully you can see here, I asked what would have to take place in order for that to occur. Well, you can see what this says is that the work net would have to be negative 3.75 joules in order to get that to happen. Another way you could look at this equation that shows that exact same thing is, let's go back to when it looks like this. Work net equals kf minus ki. And I could do a little bit of algebra, okay? I could just get kinetic energy on the other side simply by adding it to both sides, right? And you would end up with kinetic energy initial plus work net equals kinetic energy final. And what you would see is, hey, if I start with 3.75 joules, what would I have to do to stop? Well, the work net would have to be negative 3.75 joules, and it would bring me to a 0 joules, or I would be stopped. Make sense? This equation here, okay, this equation here is essentially this. Hey, what's the energy initial? Plus the change in energy will tell me how much energy there is final. How we doing? See, these are the eyes. This is what I'm talking about. It's fair. That's fair. Okay, do you understand this equation right here that I'm talking about? Okay, this is saying, like, what I'm trying to show you is that this equation is literally anything. Take the initial of something, add how much it changes, and you get the final of something, right? I have 3 jelly beans. I add 5 to the jelly beans. At the end, I have 8 jelly beans. I have 3 jelly beans. I eat 2 of them, or I decrease it by 2. I'm an end of 1 jelly bean at the end. The temperature outside is 20 degrees. Over the course of the next few hours, the change is 8, so the final would be 28, right? So I'm trying, I know it's not super easy, but trying to get you to see that this complex equation is essentially just take the initial, add how much it changes, and that tells you how much there should be at the very end. Make sense? Okay, now let's see if we can't use this. Let's get rid of this, this, and this. Okay? And let's, instead of get it to stop, let's say I do the following. Okay? Let's say I shove it to the right with 120 newtons. Spainhour shoves. Okay? While I push it to the right, there is a resistive force of friction, which kind of makes sense. Friction is 5 newtons. What I want you to do now should be review from the last 3 days. It's nothing new. I want you to find the work net. Now, there are 2 ways we talked about on Friday of finding the work net. The first way is I asked you a ton of times. Sorry, this is not okay. There, actually, you can't see it good. Is I asked you a bunch of times last night. Find the work of every force. Remember me doing this a bunch? And if I had you do that, how would you get the net work? Literally just add them up. That's the first thing that you can do. Okay? So what I said on Friday is that you can get work net by going work of 1 plus work of 2 plus work of 3 plus, you got the idea, work of 4, dot, 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 for as many forces as there are. What did I say the second method was for finding work net?
Some forces times displacement times the cosine, the angle.
Essentially, we just use the equation for work again, but instead of work, instead of the individual work, we talk about the total work. By talking about an individual force, we talk about the total force in order to pull that off. Either one of the 2 of these will calculate the correct answer for you. So go ahead and try to do that now. I will show you both methods up on the board. Okay, so you are trying to find the work net if I push with 120 newtons, and there's 5 newtons of resistive force. What should you probably be, if you're confused right now, how should you probably begin? Force diagram, correct. I've done most of the force diagram for you here, but obviously there's a few other pieces. I told first hour this already, so I'm going to stand by it for you guys. I have moved, this assignment was originally said to be due tomorrow. I have moved that to Wednesday because we were a little bit behind last week as well, although tomorrow is still going to be the lab, so we're not too behind on days. We're just going to have another day for that homework assignment.
I swear I was looking at you confused. I tried to do the homework.
It's okay
assignment.
if you are.
Well, no, I tried to do the homework assignment, and this was covering what my questions were.
Sure. And that's good. That's good. Okay, look, let me say this as well, okay? I need a class that talks to me, that is honest with me, because like first hour right now isn't saying anything, and I'm really struggling. Because it's possible, and I told them this, it's possible that your eyes aren't actually confused eyes. Your eyes are like, this is stupid boring. I get all this. I need to know that too. Like, I doubt that's probably the case based on prior examples, but like, if you get it, let me know. If you don't, let me know. If you don't let me know, I've got 2 options to solve it. If you don't let me know how you're confused, my first method is guess, which is almost always wrong, or explain it all entirely from the beginning, which so far has taken about 4 days, which I can't do. Yes, go there first.
Okay, so say we're using the first one, like the work net
Yes.
plus all the other works.
Mhm.
So would friction be a work and like normal be a work
So
and gravity
remember what we
be a
said.
work?
Work has 3 situations. So it needs to be a force. So basically what I would say is exactly what you just said, is that for every force, pretend there's a possibility of doing work, right? We know, oh, I'm sorry. Oh, shoot, I didn't give you enough information. I did this first hour too. Let's say it goes 0.8 meters. I'm so sorry. I'm so sorry. That, see, this is yet another reason why you would be confused, and totally my fault. Is that what both of you guys were going to ask? I apologize. I did that same thing first hour. I'm so sorry. So, sorry, let me put that a little bit differently, Nick. Basically, if it's got a displacement, which it definitely does, which is how I just got confused there, replace that myself, and there's a force, you've knocked out 2 of the 3, so the only thing left to tell you what there is work or there isn't is the angle, or whether or not they're next to each other. Please feel free, especially right now when you're trying to go fast, and use the shortcut for the kind of 0 simpler ones.
Well, because that's slowing it down, so it's negative. So if you, which is equal to well, that could be wrong, but I think it's not negative. Okay, well,
All right, so there's the first method, right? Actually, that's the second method. That's if you do this net force one. All right, there are both ways of doing it on the board.
can you walk through the second one?
Absolutely, absolutely. Do you understand the first one, or do you?
Yeah, I
Okay.
understand the first one.
So all I did for this first four, and I'll tell you this, if you want to go a little bit faster, I will tell you actually, usually what I'm going to do moving forward is not do them all individually, but I will start with this equation right here, and I will show them canceling rather than do that right there. And then I'm probably going to plug both of these equations just straight in there to go straight for the answer as opposed to doing them all individually. But this is me finding the work of all of them. Those are both 0. Both works are 0 because they're 90 degrees to the displacement. Work normal, force normal is up. Okay, the displacement is that way. 90 degrees means force normal is not doing anything for the work. Gravity, straight down, right? Displacement is 90, sorry, I'm not doing it perfectly here, but also 90 degrees, so not going to do any work. So what I did in both of these two cases, okay, is I just plugged the equation force times displacement times cosine theta. In the case of Spain-Hour on box, I told you it's 120, the displacement is 0.8, and the cosine, well, the angle would be 0, so cosine of 0 would be 1, giving me that the Spain-Hour on box put in 96 joules. Good so far? Friction, 5 newtons. Don't forget, because this is a big sticking point for a lot of students, remember when you use the work equation, both the force and the displacement are going to be positive magnitudes. Okay? We are not concerned with their, like if friction is technically in the negative direction, that should not be negative there. The negative will always come from the angle right over here. You'll notice if you put the negative for force and you do this correctly here, if those are going to cancel, telling you that friction is adding energy to the situation, which doesn't make a whole lot of sense. Make sense so far? So these things, 1, 2, 3, and 4, are the works of the 1, 2, 3, and 4 forces. I didn't finish the force diagram over here, so let's do that just real quick. This should be force gravity down and force normal up. Okay. And then right here, I get the work net is the work of just all 4 of them added up. I once again showed that those were 0. That was 96 plus a negative 4. So I got 92 joules, just the same as I got over here. Now, I'm showing both methods. You do not, at all, have to do both methods, but You probably should know from both of them because sometimes one is easier than the other. I would argue in this particular case, the first one is easier. It's a little bit faster, but you will note that that's not always the case. Questions on any of that? Okay. So now we've got the work net. What do I want to do with that? Well, if that's the work net, what should the final kinetic energy be of this box? Well, it started off with 3.75 joules. The work net tells us what? The change in energy is going to be 92. So you could probably do this roughly in your head. If this is 3.75 joules that it starts at, and it changes by 92, how much energy does it have at the end? What do you got? 95.75. Just literally adding the two together, right? I'm going to show you now that same thing, obviously very simplistically put, with the equation that we're using. So what you just technically did is you used the work net kinetic energy theorem. Okay? This is a cool equation because it's short, but a super complex equation because I've argued before it's a lot like a transformer. There are pieces inside of pieces inside of pieces here. So like change in kinetic energy expands out into kinetic energy final minus kinetic energy initial. This work net expands out into all that you did over there on the right side. We don't have to do it now, obviously, because you've already done that. But what you just did is, like I showed you a minute ago, if I move kinetic energy over, what you got was the kinetic energy initial is 3.75 joules. It changes by 92 joules, and therefore the kinetic energy final is 95.75 joules. Let's say I wanted to know how fast that translated to. What would I do then? What would I need to do?
You just plug it into the first equation.
Right. We would set that equal to 1/2 mass velocity final squared and just do some algebra. Go ahead and do that now and calculate how fast is the box going. When we get to complex stuff like this, I feel terrible because I've sat where you've sat and know it's confusing. And I know sometimes like your questions are like, I don't even know what I have questions about. Couple things to remember, okay? If you can help it, do the algebra on that equation without numbers first. It's going to be faster. It's going to be cleaner. It's just better for you. So let's humor me real quick. What am I going to do to find speed? Algebraically, what should I do? You could either divide off 1/2 mass. You could also multiply by 2 on both sides, but that also works. So kinetic energy final divided by 1/2 mass. I like it. Then what? Square root. And so you should end up with 95.75 joules divided by 1/2 times 30 kilograms and square root that.
What if you multiply it by 2?
It's going to be the same thing. Dividing by 1/2 and multiplying by 2 will give you the same answer. Like 4 divided by 0.5 is asking how many 0.5s fit in there. 8. 4 times 2, also 8. It's going to be the same thing. The main thing you got to remember here is you're dividing by 1/2, not multiplying. Or what I would probably do if it were me is I would go 30 times 1/2 to get 15 and just take 95.175 divided by 15 and then square root. What'd you get?
0.5.
Decimal should be a little bit off of that, I think. It's 2 point something. I think it's like 2.3 something, if I'm not mistaken.
I thought 2.5.
Did you?
2.5.
Is that right? 95.75 divided by 15. Square root. Oh, I'm sorry. 2.53. Like this. That's great. Yeah. I thought there was something else. That's great. Okay. All right. Let's do one more thing with this. Now, what I've tried to show you in this problem so far. By the way, this problem is a verbatim problem directly out of your textbook. So you can look at my stuff. You can also look at the text to show you the exact same sort of things here. But, so what I've tried to do is I've tried to take a single problem and break it into 3 sections. The first section being, hey, find the kinetic energy initial. The second section being, find the work net. And the third being like, all right, what's the final kinetic energy and what's the final speed based off of that. But you're usually not going to get problems like that. So let me give you another problem here that you might see from the very beginning. Okay, so let's say I was pushing for 0.8 meters. Okay, let's say all of this happened. Okay, and now we're over here. The box is now traveling at 2.53 or 2.5 meters per second. Okay, and the question is, if I stop pushing and the conveyor belt turns off, okay, what should the box do for starters? Slow down probably until it stops, okay, because of friction, right? Let's assume that the friction that I'm discussing that's going to bring it to the stop is exactly the same as this 5 newtons right here. And the question is, how far will the box slide before coming to a stop? Now, I will tell you the truth in this stuff. Usually, well, you could do forces to get acceleration, use acceleration and kinematics to get the answer to this, not using energy at all. I want you to use the energy here. So how would I begin this problem? Again, we don't know it's 0.8 anymore. The question is, how far will it slide at that? If it started at this particular speed, at this particular energy, how far will it slide before coming to a stop? What I said is that this equation is kind of your beginning equation. So let's go ahead and do that now. Just write this out right here. Now our force diagram is almost exactly the same except what? The 120 is gone. Otherwise, it's exactly the same, right? So let me show you how I would now usually do this problem, okay? What I would do is I'd start here, and then basically these expand outwards, like I was talking about transformer-wise earlier. Let's start with the easy one. How does this expand outwards? No, not quite. Change. So this would be...
the final minus the initial.
Correct. Keep in mind that there's 2 1/2 mv squareds in here. Next, let's go to the left side, work net. I can expand this out in one of 2 ways. Either I can make work net equal to this mess, the net force times displacement times cosine theta, or I could make it equal to all of them added up. I'm going to do the second one here. Meaning, you look at your force diagram and you go, all right, if it has a force, I'm going to go work of normal plus work of gravity plus work of friction. If there's a force, it technically has the possibility of doing work. Now from here, see if you can't discuss quickly in your group. 3 of these cancel. Which of them cancel to 0 and why? Discuss real quickly in your group. We'll be right back after this message. All right, what you got? Gravity, work of gravity will cancel. Correct. Why do both of those cancel? The force is perpendicular to the displacement, yes. Okay. Now note that these guys will cancel for different reasons. Well, these 2 cancel for the same reason, but the left side is going to cancel for different reasons than the right side. What cancels over on the right side and why? Correct. So these will cancel because of the angle between force and displacement. this will cancel because of the speed at the very end, leaving you with an equation that makes sense, and that's this. Does it make sense that work of friction is the only thing changing the energy in this situation? Yes. Does it make sense that the energy is going to reduce by however much we started right here? Yes. Now, the other piece of this puzzle is you kind of got to learn when to expand it out and when not to. For example, this right side, we know that's equal to 1/2 mv squared, right? But why would that kind of be dumb to put that equation of 1/2 mv squared? I know the speed, right? The speed is 2.53. Why would it be dumb to replace that with 1/2 times mass times velocity squared? Correct. We already know that kinetic energy is 95.75 joules. Why would we get an equation to try to find it when we already know specifically what it is? Now, what was the original question? Now, I don't see displacement up here, but what is it buried inside of? Where is displacement buried inside of here? Correct. So this is an equation I'm going to kind of expand outwards. So what?
How is the displacement in the work of friction?
What's the equation for work? So if I instead of work friction, if I put its equation, what is the equation for all work?
Force times displacement times the cosine.
And that answers your question. Now, whenever angles are easy, 0, 90, and 180, I'm completely fine with you not plugging in cosine of 0, cosine of 90, cosine of 180, but instead quickly simplifying, what is the angle here?
No. 0?
No.
180.
180, because the displacement is this way and the force is the opposite direction. And what is the cosine of 180? Negative 1. So I put an arrow here. Usually we've been going up to 0. I'm going to put an arrow to negative 1. And that negative 1 is going to nicely cancel with?
The negative on the...
Correct. The negative on the other side. Leaving me with arguably a very simple thing to do, although somewhat confusing. What do I now need to do to get displacement? Displacement is going to equal kinetic energy initial divided by force friction. What is kinetic energy initial?
95.75 joules.
And what did we say force friction was?
5 newtons.
And this units-wise makes sense because this is joules, which if you remember is Newton meters. So if I divide by newtons, I should be left with just meters, giving me the answer of 19.2 meters is how far it will slide. Real quick, humor me, and I know it's confusing. Give me a 1 to 5. How comfortable do you feel about work net kinetic energy theorem right now? Okay. Make sure you try the homework tonight, even though I know it is due in 2 days on Wednesday. All right. If you have any questions online, please email me. Let's see what we can do for it.